Writing the rate law implied by a simple mechanism, or not so simple in this case, okay? So our problem here is we are told the first step is much faster than the second. That means the second step is the rate determining step. So the problem is that our rate law for our overall equation will match the rate law for the rate determining step. And the rate determining step has if it's the second step, it's going to contain the intermediate as one of the reactants. So we can go ahead and write the rate law for step 1. So it's K1 times the concentration of NO times the concentration of chlorine, and we can do the same for step 2. The rate law for step 2 is K2 times NoCl2 and the concentration of NO. So therein lies the problem. This NoCl2 is an intermediate. It is formed at the end of elementary step 1 and it gets used up at the beginning of elementary step 2. Now, we've met intermediates before because we know that is the key to being able to balance any multi-step reaction. So the way we do it is anything that is on the left-hand side of the arrow in each elementary step will be on the left hand, the reactant side in our overall balanced equation, and anything on the right-hand side of that reactance arrow will be a product in each elementary step. Also, is going to be a product in our overall reaction. But we use the same rules of mathematical equations. So if we have like terms on the same side, we can gather them up. If you have like x plus x on the left-hand side of the equation, then that's just going to simplify to 2x. Similarly, if you have the same term on both sides of the equal sign, if you have like plus 2y on the left side of the equals and plus 2y on the right side of the equals, then the 2y is going to cancel, right? So same deal with chemistry. In order to balance these equations, we look at the intermediate. The number of moles of intermediate that is getting used up in the subsequent elementary step can only come from the product side of the preceding elementary step. So we have to make sure the number of moles of intermediate match so they will cancel out in the overall balanced equation. So that is our key. If it is unbalanced, we need to multiply one or both elementary steps by an integer in order to get that intermediate to cancel out. So I'm going to go ahead and I'm going to type out all the things that are on the left-hand side. So from step 1, that's nitrogen monoxide and chlorine. And then from step 2 is our intermediate NoCl2 gas, and then plus another NO gas. And then on the right-hand side, from step 1, our products are going to be our intermediate again, NoCl2, and then from step 2, we have 2-nitrosyl chloride, NoCl gas. So we can see that our intermediate will cancel out, and we can also gather like terms. We can gather our nitrogen monoxide. So our overall equation should be of the form 2NO gas, state symbols are important, plus Cl2 gas goes to our product, nitrosyl chloride, NO, whoopsie, NOCl, and that should be balanced. Okay, so the experimentally observable rate law, we're going to have to take a few steps. So the trick for this is we're actually going to write the rate law for the reverse of step 1. So the reverse of step 1 is going to be the decomposition of our intermediate NoCl2 decomposing into nitrogen monoxide and chlorine. This will allow us to write the concentration of our intermediate in terms of the concentration of our other reactants. So I'm going to call this rate law rate -1. So I'm being consistent with ALEKS, and that's for the reverse of elementary step 1. So that is going to be K, the rate constant of the reverse reaction for step 1. So K -1. And that is going to be the concentration of NoCl2, and it will be first order in that reaction. So then what we're going to do is we're going to use what we know about dynamic equilibrium. So when the state of dynamic equilibrium is reached, that means the rate of the forward reaction is exactly equal to the rate of the reverse reaction, or as we wrote it, rate of elementary step 1 is exactly equal to the rate of the reverse of elementary step 1. Okay, so we can go ahead and then we can write rate for elementary step 1, which we wrote as K1 times the concentration of nitrogen monoxide times the concentration of Cl2. And then the reverse of that is K minus 1, and that will be multiplied by the concentration of NoCl2, our delightful intermediate. So now we are at the stage where we can rearrange and have the concentration of our intermediate in terms of our concentration of nitrogen monoxide and chlorine, so our reactants from elementary step 1. So that is going to take the form NoCl2 is going to be equal to K1 over K minus 1, so rate constant for the forward reaction divided by rate constant of the reverse reaction, times nitrogen monoxide times concentration of Cl2. So now we can take this and we can substitute it into our rate law for step 2. So we're going to make this substitution right here for NoCl2. So let's do it. So rate for elementary step 2, which should match our overall balanced equation, is going to be K2, and then we're going to substitute in what we just found out for the concentration of NoCl2 in terms of all your other stuff, okay? So K1 over K minus 1 times the concentration of nitrogen monoxide times the concentration of Cl2. So that is our substitution right here for the concentration of our intermediate, and then all that has to be times by the concentration of NO. Okay, so we can tidy this up a bit. We can tidy this up a lot, okay? So first of all, okay, we're going to come back to this guy right here, but this is just an equilibrium, sorry, a rate constant. So a constant is a constant is a constant. We can just call that K, and we can also tidy up these nitrogen monoxides here to first order concentration nitrogen monoxide is the same as writing nitrogen monoxide squared. So my rate is going to be K times NO squared. I should probably try and tidy this up a little bit. Hang on, let's move it up. NO to the power of 2 times the concentration of Cl2. So now the rate law for my elementary step 2 is all in terms of my initial reactants, nitrogen monoxide and chlorine. So that should be okay. Then the last bit is asking, so this rate constant here that I used, what was it really? So that is going to be this stuff right here that we just worked out. So it's going to be in terms of what we said, it was K2 times K1 over K minus 1. So like I say, quite often I use KF for the forwards reaction K1 and KR for the reverse reaction K minus 1, but I'm trying to keep to the terms that ALEKS uses. Okay, so hopefully that will help you deal with situations where your second step is the slow step, so your second step is the rate determining step, and your issue is that you have a concentration of the intermediate in there, okay? So you have to make sure you can write the concentration of the intermediate in terms of the concentration of your actual reactants. All right, take care, ta-ta, bye-bye.